All right, so T and B cells. They're nervous, some people, right? So T and B cells. When we look at T and B cells right here, I don't know, I didn't just move it here. All right, in terms of T and B cells, T cells are going to have a specific receptor. Now, we have two categories of T cells: helper T cells, cytotoxic T cells. Now, cytotoxic T cells, the name should kind of help us understand what they do. Helper, they help, right? They don't kill anything directly. Cytotoxic T cells, cyto for cells, toxic. So it's going to be toxic for the cells. So these two types of cells make up our T cell receptor, or make up our T cell class. Each one of these T cells, whether it's a helper T cell, each one is going to have a specific T cell receptor that recognizes a specific epitope. So think of a lock and a key. You guys have probably seen all the different lock combinations that we have. Now, one of the problems we see at work is all of our keys look very similar, and all of them look very similar. And to make it even harder is all of the grooves look very similar. So what happens? How can one key open up only one lock right here? Is because grooves are so specific that when it enters, let's say I have the key for this door, when I have the 639 key, right, it sounds, it almost looks identical to what it should. Goes into the actual lock. It even starts to twist it, but not all the little tumblers match, right? Not all the little grooves match all the different tumblers that are found in the lock. So it doesn't open. Now, if I have a BL key, every single groove matches all the different, right, parts of the lock. When that happens, I can twist it completely and unlock the door. In other words, there's a lot of specificity in these keys and these locks. There's even an incredible amount of specificity. So I have these T cell receptors, and they're going to be very specific for a given shape of an epitope. And the shape can be something that is triangular, right? It's a shape of the proteins that is expressed that's important. Now, cytotoxic T cells also have T cell receptors, and they recognize specific shapes as well. Now, let's say we just give it herpes zoster virus A, protein A. That's what it recognizes. Both of them. So if it encounters anything with a match for herpes zoster epitope A, it can bind to it. Perfect. So if you have a virus here, and that virus comes in, and it's got an epitope A sticking out of it. Now we have a match, right? The epitope displayed matches the actual protein receptor found on our helper T cell. Now, the weird thing is this: with specific immunity, especially with T cells, they cannot self-activate. Meaning, in order to activate, they need to be presented, that actual epitope, by another cell. So that's where we start talking about, MHC 1 and 2 again. All right, now again, on this one right here, keep in mind that, again, there's a three-dimensional shape for these epitopes right here. That three-dimensional shape for the epitopes right here means that there should be a matching anti-shape for the receptor. Now, the book and a lot of textbooks, not just ours, a lot of textbook will switch back and forth between using epitopes and then antigens. Epitopes and antigens. When they're talking about specific recognition areas, I want you to think epitopes, even though they say it's antigen. When they talk about the larger virus, the larger bacterium, right? Even a larger toxin, then I want you to think is the antigen. Antigen is something larger, right? On an antigen, you'll see multiple epitopes. So here, this is the larger antigen right here. These are all the different combination epitopes found on the larger antigen. Activation can occur in two ways. T and B cell receptors combines directly with the antigenic determinant. Activation also involves glycoproteins called MHC molecules. These molecules attach to the plasma membranes, have variable region that can bind to foreign and self-antigen. So what we're going to see is this. We just said that we have these T cell receptors that all these T cells have that make it specific. Now I'm talking about MHC. What does this mean? Right? Now MHC are just signaling molecules. It's a way of signaling that this cell is part of my larger protein or my larger body. So MHC1. In MHC1, we're going to have a receptor and it's going to display host protein. Displays host proteins. That means your proteins. And it's found on all nucleated cells. In other words, my helper T cell, my cytotoxic T cell, those all have MHC1 receptors. And it's going to display my protein over here. I should make it that. And it's going to display a protein my body makes with specific tags that says this comes from my body. So it has my protein on it, and if I have another white blood cell coming here, my white blood cell that kind of makes sure my helper T cells isn't malignant, it's able to kill it and fight it, right? Or let it live and let it survive because it's part of my cell, right? Since it's displaying my protein, that means my helper T cell hasn't been infected with anything. It's normal. Should I have a white blood cell kill this cell? No. If it does, that's an autoimmune disease. Your white blood cells should never kill any cell that's displaying a normal host protein. Right? Now, there are times when we need to kill a cell. A cell's getting old. We need to make sure they die, right? And it's not necrosis. That's programmed cell death. That's usually not caused by another cell. Is that cell just kind of dying off by itself? Apoptosis. All right, so we have this MHC1 found on all nucleated cells, found on our helper T cells, found on our cytotoxic T cells. Also found out on our macrophages. The macrophages are really important. Macrophages, right here, have our MHC1 and MHC1 displays my protein, just like every other cell, right? All nucleated cells need that display to signal that this is a normal, healthy cell. Don't attack me. Now, what makes macrophages, and usually macrophages, we just wrote it like this, because it's a long name, right? So what makes macrophages and even B cells very important is that they have a different category of MHC receptor, MHC2 receptor. MHC2 receptors are only found on all macrophages. That means monocytes. That means Langerhans cells in our skin. I know you guys wanted to forget that one, right? Good old Langerhans cells, right? Yeah, right? How about glial cells, right? Remember the glial cells in the central nervous system? Yeah, right? Immune cells, right? So, yeah, you guys all remember. I can see it in your face. And all of those cells, those are all types of macrophages. So all macrophages and B cells have a second category of receptors. And those second category receptors are called MHC2 receptors. So it has MHC1 that says, I'm healthy, I'm displaying this good host cell, don't attack me, right? That's true for all nucleated cells. Then MHC2 are found in specific ones that are macrophages and B cells. They have a second category of receptors, right? Those receptors, MHC2 receptors, is what makes these guys antigen-presenting cells. So we only find it on these cells, macrophages and B cells, but we only find it on here because they're the only ones that will present an antigen. What we're gonna see is, for us to activate this guy right here, my helper T cell, the helper T cell cannot just bind to a virus. Can't do that, right? Not to activate it. What it needs to do, this helper T cell, is that in order to get active, it has to be displayed, that epitope. So let's say you have a virus right next to this helper T cell. That virus has that epitope, varicella zoster epitope A. It recognizes that epitope. So everything is a match, right? Perfect. Well, what happens is, even if the virus is right next to it, that virus cannot bind to that receptor, right? It can't bind to it. So it needs to be displayed by a macrophage. Once a macrophage swallows up the virus, the macrophage will kill that virus, and then it will display all of the epitopes. And one of those epitopes is bound to be varicella zoster epitope A. Once it's displayed, that's when this guy can recognize that epitope. Weird, right? You imagine the virus is right there. Why can't you recognize it? But it cannot recognize it while the virus is just free floating around. It needs to be displayed a certain way for the T cell receptor to recognize. So what happens here then? Well, what happens is this. You have a varicella zoster virus right here. And I use varicella zoster just because it doesn't mutate. And here's their epitope A. What happens? Macrophages are going to go around, macrophages right here are going to go around, swallow up the virus, and then it's going to display all the different epitopes on all the different MHC2 molecules. So you'll have an epitope A right here. Then you'll have an epitope B. Then you'll have an epitope C. You can have thousands of different epitopes on the outside of this virus. What happens? The macrophage swallows it up. As it swallows it up, it kills, right? It kills the virus. As it destroys the virus, it's going to start putting all these different epitopes on different MHC2 molecules. So then you'll have epitope A over here. For varicella zoster. Now it's displayed on MHC2. So MHC2 receptors will only display foreign epitopes that have been processed from destroyed antigens. So macrophage goes around, it notices that you have a virus there, swallows up the virus, kills a virus. Now, if you just kill one virus, what have you really done, right? Nothing, because you're gonna have billions and trillions of viruses just floating around. Killing one isn't gonna do anything. But what that you can do is you can alert other cells. And what happens, as it swallows it up, it starts displaying all these different epitopes. Epitope A is displayed. Epitope B is displayed. And then epitope C is displayed right here. All these epitopes are displayed. As they're displayed, what we're going to see, Once you display it, we get rid of all the content. We don't need it anymore. We kill out the virus. And what we're going to see, what happened to my black one? Right? Just ended it right here. What happens is now we have all these different epitopes sticking out. Thousands of different epitopes and thousands of different MHC2 molecules. What does this mean? It means that you have thousands of different cells you can activate, right? Thousands of them. So what we're gonna see is that once a macrophage swallows up a virus, it moves into your lymph nodes. As it moves into your lymph nodes, the macrophage displays all these different epitopes in a 360-degree array, all the way around. And what we're going to see is that all of these virus, epitopes are displayed, so then lots of different helper T cells can see they recognize one of them, right? That's why what we're going to see is that when we looked at a lymph node, and that's way back in 201, when we look at a lymph node and reticular tissue, usually with the reticular tissue, we saw that there looks like there's like clusters of cells that surrounded something in the middle, right? A circular arrangement of these cells. Well, what happens is this. You have the macrophages in the middle of the cluster. And then you have all these helper T cells surrounding it in a circle, seeing if it recognizes any of the epitopes. If it recognizes any of the epitopes, it can fight off the infection. It can become activated. So what happens? This helper T cell comes around. As this helper T cell comes around, right here, it recognizes this epitope displayed to it, right? And when that happens, now I'm gonna cheat because this guy's right here anyway, so I'm gonna switch this into a helper T cell because that's so close to it, I don't wanna have to erase it and redraw it. So this is a helper T cell, they just kind of switched. What happens? This helper T cell then has a T cell receptor that recognizes that epitope being displayed. When that happens, you have specificity now. If this helper T cell, instead of having something that recognizes it, has a receptor that kind of look like this, what happens? Well, the T cell receptor, the shape doesn't match the shape that's displayed to it. When that happens, there's no activation. Why activate cells that don't recognize what's invading you? There's no reason to do that, right? You're just gonna waste energy, waste time. And the cells that you produce won't help fight off the infection. So we only want to activate cells we know recognize what's invading us. So this cell doesn't recognize it, it doesn't get activated. But this cell that has a matching receptor with a matching shape does recognize epitope A, right? And when it does, the macrophage right here stabilizes it. As it stabilizes, it starts releasing an immune message called interleukin 1. Interleukin 1 goes into the helper T cell, activates the helper T cell, but only if there's recognition. So you have a lot of what we call co-stimulation. I've read the actual articles on this. There's like 7, 8 different co-stimulants, right? So not only do you have B7 having to match with CD820, there's a lot of these where you have to have all these different matches right here. So here's this co-stimulation between the macrophage right here and the helper T cell. So there's probably a better picture. I know it's hard to imagine. But if you take a look, the important part here is that there is a recognition.